Hello everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
As I said, we are going to carry on our series on statistical tests, how to do them, roughly what they are. Try and keep it simple. As I said numerous times now, I'm not a statistician or an expert in statistical software. I just like to play with these things. And I find it quite useful in my career, so I thought I should share it with you. Let's have a quick look at what we talked about last time. So last time we talked about assumptions. For a very quick refresher, an assumption is basically something you assume to be true about the data you're analyzing. And it has to be true in order for that particular test that you've chosen to work properly. And the two assumptions we talked about last time were normality. That is to say, the data follows a normal distribution, and scarcity. That is to say that the samples that you are comparing have a comparable variance. And I hope all that sort of sounds familiar after the talk from last time. We talked about students T. Now, just a brief refresher, students T, when you have two continuous variables, is a test that you use to determine whether those continuous variables belonging to two different samples are statistically significantly different or not. And I showed you how to run it with Jamovi. Now, as we said last time, the plan is to carry on talking about continuous data. We're still talking about normally distributed data. And today we're going to talk about ANOVA, or analysis of variance. And again, we're going to do that with Jamovi. Usual QR code if you want to snap it to have a look at the Jamovi website. Great software, completely open source, freely available to run all your stats on your own. Very user-friendly, as you will see. So let's talk about ANOVA. ANOVA is one of the many products of Fisher. Now, Fisher presented a work related to analysis of variance back in 1921, when he was working, guess on what? On crops, similarly to what, well, student, so to speak, was doing. Now, Fisher is famous for a number of things. If you have a look on Wikipedia, this is the list of things he's known for. Some of them, and quite a lot of them actually, have to do with statistics and math. And he's kind of considered one of the fathers of biostatistics, really. We still use his tests routinely, Fisher's exact test, etc., and a number of others. He's also slightly less glamorously famous for his positions on eugenetics, but I will leave you to dig into that on your own time. If student T was about two samples of continuous variables from two populations, ANOVA generalizes that to more than two. So if you have three or more samples representing three or more populations, you're asking yourself, how do I know if these three different samples really belong to three different populations and are truly different from each other? A typical example that Fisher was coming across was, well, I have three fields of barley, and I've given each of them a different fertilizer. And I want to know if the barley that comes out is better with one of them, or different anyway, or if the actual fertilizer makes absolutely no difference whatsoever. And that's kind of where all of this is born, so to speak. And the key concepts that you need to grasp to understand how ANOVA works are within group and between group variability. So you have a batch of barley. Within that batch of barley, there'll be some grains that are better than others. There will be variations within that group, and that's called within group variation, and is measured through variance. So a mathematical variable associated between, but basically is calculated from the difference between each value and the mean within that particular group. The second important thing to remember is between group variability, which basically means what's the difference between the different means of the groups. So if I got 3 groups of barley, each of them will have a numerical mean for a particular value. What's the difference of the mean of group 1, 2, and 3? Okay. And if you want to represent it graphically, between group variation, again, has to do with the difference between the different means of each population you're considering. If you're looking at within group variation, it has to do again with the variance within that particular group. Does that make sense? I hope it does. But feel free to pop a message in the chat if I'm talking complete nonsense and you don't understand what I'm talking about. So, bottom line, ANOVA works because for a certain amount of within group variability, you expect a certain amount of between group variability. So if really you have 3 batches of barleys that have been taken from the same field, you would expect that their variance will be similar, although it will not be identical, and that to the variation within each of those 3 samples of barley, because they come from the same field, will correspond a certain degree of variability in the means of those 3 groups. If, on the other hand, the 3 batches of barley have been taken from 3 different fields, have been fertilized with 3 different fertilizers, there will be a variability within the groups, but its relationship with the variability between the groups will be different. So if there is too much of variability between groups in comparison to the variability within the groups, then it means that those samples you're analyzing are actually from different populations. I hope that makes some sort of sense. Sorry. So, as we said, when we run a test, we look at assumptions. Normality is still very important. We talked about it last time. We're going to talk about it again. Whenever you're running this particular type of test, ANOVA, you're assuming that the continuous variables you're analyzing lie on a normal distribution. You're also assuming that their variances are relatively similar, so they are almost stochastic. Now, I appreciate that some of this concept I've elaborated on a lot in the previous session, so I'm not going to go into details, but please remember they're very important, and I'm happy to elaborate after the presentation if you want me to explain it again. There are other assumptions. Obviously, the samples are randomly selected. The sample needs to be big enough. How big is big enough? That's always difficult to say in statistics, and there's different opinions out there. And obviously, they need to be independent from each other. So you're just taking them from 3 different fields or 3 different populations, okay? So, quick recap of why we're doing this. Well, we do ANOVA when we have 3 or more samples of continuous data, when the data that we've got is normally distributed, and when the samples that we have collected have comparable variances. So again, continuous data, normal distribution, homoscedasticity. So let's give you an example. As you probably recall from the previous sessions, for my dissertation, I was looking at retweet rates versus tweets published by publishing journals when they're advertising the publications on Twitter. So for the purposes of that work, I have collected data about tweets that these journals have made and how many retweets those tweets attracted. Now, in this particular scenario, I want to know if different tweeting journals affect the number of retweets that that particular tweet is getting. So again, I've got 6 publishing journals. Each of them is associated with continuous variables, which is the number of retweets. I hope that makes sense. So let's have a go. And for the purposes of having a go, we are looking at a particular type of ANOVA, which is the one I've talked about, which is one way, meaning looking at only one particular variable, that is to say the type of journal that is. We can do ANOVA in more complex ways, but we'll talk about it next time. And we will act as if the data is actually normally distributed and homoscedastic, which isn't, and we will see as we go along that it is not. So as last time, we're going to open our lovely Jamovi data set. And for those of you that are not familiar with this data set, I've kind of used it for the previous lectures. There's a bunch of papers in here, a number of variables. Some of them are nominal, some of them are scales, some of them are continuous, like retweets. So for the purposes of what we need to do, we're going to go on ANOVA, and we are going to go on one-way ANOVA, and we are going to pick our dependent variable, which is a retweet, and we're going to choose our grouping variable, which, as we said, is journal title. Now, last time when we did students T, we used surgical or medical, that is to say 2 groups. Today, because we're doing ANOVA, we've got more than 2 groups. In particular, we've got 6. There you go. And as you can see, Jamovi spits you out very quickly an output, which tells you that, yes, the journal does statistically significantly affect your likelihood of getting retweets. Now, there's a few caveats here. First of all, we are assuming that variances are equal, so we need to check that, although we know it's not true. And we're going to run some assumption checks. As we said, we need to check if the data is normal. Is the data normal? No, it isn't. But that's fine, because we're only doing this to demonstrate how to do the ANOVA. I'm not saying that ANOVA is the right test to do here. Okay, so this assumption is violated. So is the assumption of homoscedasticity. We talked about this test, Eleven's test, last time as well. And as you can see, the data is not normally distributed and the variances between the groups are different. So this is not the right test to run, but I've shown you how to run it for the purposes of doing your own stats at home. Next time, maybe we'll talk about how to do or what to do when your data is not normally distributed, but you still need to do an analysis of variance. So there are variations like Welch test and a few other bits and bobs that luckily Jamovi lets you do, which again is a wonderful software. So look into it, just play with it a little bit. And I'll call it today. I've taken about 15 minutes, so I hope it wasn't too tedious or too complicated. Thank you.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.